Good evening, everyone. Welcome to the Alumni Lecture. My name is Merel Ritsma and I will be your host for tonight. We are going to listen to Professor Dr. Arno Kentgens, who is unfortunately forced to give his lecture from quarantine. I'm personally also dealing with a severe cold, so excuse my very nasal voice. Before we start, allow me a quick introduction on Professor Kentgens. Arno has been connected to Radboud University for a long time, first as a student, then as a PhD candidate. He has been away for only 1 year for a job at Philips and then quickly returned to Radboud to coordinate the National Nuclear Magnetic Resonance Research Facility. Het Goudsmit Paviljoen is home to this facility and it can be found behind the Huygens building located inside a pond. Here, Arno is leading the research in a European infrastructure. In his lecture, Arno will explain how NMR works. He will talk about the history of the research on NMR, and he will discuss possible applications of NMR. Feel free to ask questions in the Zoom chat. There will be time to answer these at the end. You are also very welcome to ask your questions at the end by unmuting yourself. Please raise your hand and I will give you the floor or the screen. This meeting is recorded, but as long as your microphone is muted, you won't be in the picture. For Arno, it would be nice if some of you would like to enable their video so he is not just talking to his screen. So let's switch to Arno now. Thank you for listening to this introduction and enjoy the lecture.
Okay, thank you, Merel. So it's a pleasure to be able to give this lecture. But yeah, as Merel already said, I'm doing it from my study as I'm in isolation at the moment. So it's a pity that we can't do it live. But well, I guess we have to save that for a later time. So let me start with sharing my screen. This is the so-called Goudsmit Pavilion, where my lab is housed. And I will tell you in a second why it's called actually the Goudsmit Pavilion. And what I'm going to do tonight is I will tell you a little bit about the discovery of spin. I guess I think I have a rather diverse audience, and the concept of spin, as it is related to quantum mechanics, is always a bit of an issue. But that's actually working with spin is the workhorse of what we do with NMR spectroscopy. So I tell you a little bit about the background. Also, this is a historic year, as I will tell you. Then I'll tell you about what specifically solid state NMR can do, but I will do that in the context of applications to energy materials. And we have a few examples of systems that we are working on in the lab. I don't know if I have enough time to treat them all, but we'll just see. After about 45 minutes, I will just stop talking. And then I hope that we can have indeed some discussion after that. So first we have to go back to the beginning of last century. And that was when quantum mechanics was developed. Yeah, here is a picture of the famous Solvay conferences with many great names there. Of course, we see Einstein in the front middle, Madame Curie, we see Lorentz, Planck, Born, and here we see Niels Bohr. And Niels Bohr was developing his model for, the atomic structure, where he discussed about the atom looking like a planetary system with this positively charged nucleus and the electrons orbiting around it, but only in very specific quantized orbits. And well, there was a lot of discussion. And as we know now, I mean, it's a nice star, but that's not entirely correct. But from the fact that you would have these orbiting electrons, when an electron orbits, of course, it also generates a small magnetic field. That comes from the orbital angular momentum. But in that way, you would get a quantization in space. And exactly 100 years ago, so it's really, I think it was February 1922, Stern-Gerlach set out to do an experiment, finally, that they discussed a lot, to disprove the Bohr model and Bohr and this so-called spatial quantization he introduced. But actually, they did prove for the first time that quantization can be observed directly. So what they did is they, in an oven, they generated a beam of silver atoms. They led that through a inhomogeneous magnet. It's specific a magnet with a field gradient. And then they were detecting the signal on a glass plate. And the idea was that you would then see just a nice distribution of the different atoms being deflected in that field somewhat, but no discrete splits or something. But that's exactly what they saw. This is with the magnet off, and this is with the magnet on. And they thought now, okay, so Bohr was right after all. And this postcard was written to them, to Bohr, to congratulate him on the correctness of his theory. So, yeah, that sounded like a nice proof. However, it's not entirely correct. Because say the whole model of Bohr and the quantum numbers that were defined, like electrons sit in a certain shell, then there are indeed there is the orbital angular momentum, and there are certain spatial projections that can take. That was not complete, and there were quite a few issues still. For instance, with the so-called Zeeman lines, if you did optical spectroscopy. Zeeman showed if you do optical spectroscopy of sodium in a magnetic field, when you switch on the magnetic field, all the lines split. And they try to calculate that with indeed what happens to the orbital angular momentum, so the spinning of the electrons in the magnetic field, but they kept failing. And then in 1925, Ulhenbeck and Goudsmit, who were PhD students of Ehrenfest, they postulated there must be an additional quantum number, an additional degree of freedom, as they called it. And they talked about the rotation of the spin, the rotation of the electron. That would generate a separate magnetic field, and that would be an additional quantum number. And with that theory, which actually met with a lot of controversy at the time, and that is why Ulhenbeck and Goudsmit actually are the least known from all the big names that developed quantum mechanics, but they were in essence right. The numbers didn't exactly fit, but they were right. So in the beginning, Pauli opposed of that theory, but he also soon gave in a way. And actually, the Pauli principle is about the electron spin, that if you put two electrons in an atomic orbital, that they have to have opposite spin. And with that, they could explain the so-called Zeeman effect, which shows that here we see the sodium lines without a magnetic field, and here we see the fine structure that you get, all these extra splittings with a magnetic field. So Pauli got a Nobel Prize. Zeeman, of course, already had a Nobel Prize earlier, but poor Goudsmit and Ulhenbeck, actually they were left behind. But they were correct, and also now they could explain what actually happens in the Stern-Gerlach experiment. And I found a nice animation on YouTube, which is clearer than when I try to say it in my words, so it has the end. So I'm going to play that for you now.
The Stern-Gerlach experiment, performed in 1922, delivered the first experimental proof of the fascinating degree of freedom of an electron spin. A beam of silver atoms was generated in an atomic beam furnace. It was then sent towards an inhomogeneous magnetic field. According to classical physics, one would expect the magnetic moments of silver atoms to be randomly oriented. They should be deflected in the inhomogeneous magnetic field by different amounts, depending on their orientation. However, the researchers observed that the beam was split in two possible states, which were later named spin up and spin down. How can this be explained? Let us first analyze the electron configuration of a silver atom. One silver atom has a total of 47 electrons. In 46 of these electrons, each spin up is paired with one spin down. The spins neutralize each other. There is only one unpaired spin, the spin of the 5s electron. It can be either in spin up or spin down, or in any superposition of these two states. Let's have a closer look at the quantum mechanical measurement process in the Bloch sphere. The spin has some arbitrary orientation before it interacts with the inhomogeneous magnetic field. The inhomogeneous magnetic field acts as a filter. It is presented here as a slot. It forces the spin to take a random orientation, either in line with the inhomogeneous magnetic field or in the opposite direction. If the basis state is close to up, it is very unlikely to change the direction in down. However, it may still do so. When performing their canonical experiment, Stern and Gerlach were unable to use single silver atoms. Therefore, they could not demonstrate the role of chance in each experiment. However, they were the first to demonstrate that the spin is quantized, or separated in up and down. It was a sensational achievement in their time.
So, but actually, as I already said, the Stern and Gerlach themselves did not consider the spin to be responsible. That only came later. So, and then really soon after that, this existence of the electron spin was defined, it was also postulated that the atomic nucleus will have a spin. And actually all the nuclei in the periodic, say all the atoms in the periodic system, almost all of them, they have isotopes that carry a specific spin property as well. So they have a certain magnetic field related to them. And that depends on a certain ratio. It's called the gyromagnetic ratio, which gives you then, when you look at the spin, then the size of that magnetic field. And again, it's a quantized property. So when in the end you do the experiment, when you look, then you will find also the nuclear spin in a spin up and a spin down state. Now, and based on this effect, then the next step was to think about how one could study this in bulk matter, for instance. When you look at the difference in energy of this up and down state in an external magnetic field, for nuclei, you find frequencies in the radio domain, and so in megahertz. And for electrons, by the way, it's quite a bit higher. It has a much larger magnetic moment, and that is in the gigahertz range. But it should be possible to say interact with the spins in bulk matter. And actually, they succeeded in 1944. Savoysky succeeded to do electron spin resonance, and in 1945, Purcell and Bloch independently at the East Coast and the West Coast of the US, they succeeded in doing NMR, so proton resonance in bulk matter. So Bloch got the signal of the protons in water, and Purcell got the signal of protons in solid paraffin. So we already have a difference between liquid state and solid state NMR here. But it was really curiosity-driven research. And what is nice to mention is that when Bloch was asked, what is this method you developed actually good for? Well, the only thing he came up with is, well, I really don't know, but I do think it can be used to accurately calibrate magnetic fields. But I think that is a nice, a nice example of how curiosity-driven research, without the researchers knowing what is really good for, and as we all know, of course, the most important spin-off of this type of experiments is the development of magnetic resonance imaging. Every hospital has an MRI, or actually several MRI scanners these days, where we make images actually based on the principle of Bloch, where the magnetic field is varied over the body in a controlled way, and you can map out the resonances of the water and the body, and as such make images of what's happening inside the body. And on top of that, of course, NMR has developed into one of the most versatile spectroscopic tools that are used in chemistry and in material science. And that actually came about a few years later, after the discovery of the NMR phenomenon as such. Packard in Stanford, so at the same place where Bloch was, they were experimenting with this phenomenon, but at that time they had slightly better magnets already. The first magnets that were used were extremely inhomogeneous, whatever, and you were happy to see a resonance, but that was it. And Packard saw that when he put ethanol in the magnet and did his experiment, that he saw 3 lines. Each of the protons, the chemically different protons in the ethanol molecule, gave a different resonance. And essentially that is the point where the physicists more or less said, we are done, we've seen the effect, that's it. And this is where the chemists started. And actually modern day NMR as a spectroscopic tool has been developed by physical chemists. And as said, so every organic lab has a few NMR spectrometers just to fingerprint the molecules that they make. But beyond that, a lot of material science and biostructure determination is these days also done with NMR. So what is the basic NMR experiment? So you have a strong magnetic field. It's a superconducting magnet, like in this picture. So it's essentially a large coil made of superconducting wire. You cool it with liquid helium until the resistance of the wire is 0. You charge it to a certain amount, and then internally you generate a huge magnetic field, which is of the order of a few to up to 28 Teslas these days. Then when you put a sample into the magnet, all these spins, they precess in that magnetic field, and with their slight preference to be spin up rather than spin down, the energy differences are minute, but there is a slight preference. And as a result of that, the sample builds up a certain macroscopic magnetization. And what we do in an NMR experiment, we put the sample in a coil, we put on some radio frequencies, which are resonant with the spins. That tipped over this magnetization by 90 degrees. Then you just switch off your RF and you use that same tiny coil as a detector. So this precessing magnetization will actually induce a current in this coil. And essentially that is what we detect. And that also precesses at frequencies in the megahertz regime. But that is the basis, the basic workhorse experiment of modern day Fourier transform NMR, as it's called. Okay, so yeah, it has become an important technique, and here you see an overview of all the equipment that we have in the Magnetic Resonance Research Center. and the people who work there. Yes, as I said, we have magnets from tabletop systems, which these days work with permanent magnets, but very stable, where we work at frequencies of, say, 40 megahertz up to over 20 Tesla magnets, where we have resonance frequencies of 950 megahertz. And the strongest magnet available at the moment is 1.2 gigahertz even. And the Netherlands has one that we all share, which is also part of our national facility, which is called NMR, and that is stationed in Utrecht, actually. But this 1.2 and the 950 are shared instruments between the different groups that constitute this distributed national facility. On top of that, we are also organized in a European way. So also European researchers have access to all these systems. And they even get supported to come to us. What we do is we work still on the methodology. That is really something extremely remarkable about NMR, I would say, that even so long ago, more than 75 years after the discovery of the NMR phenomenon, we are still working on the methodology and how to interact with spins, all to improve sensitivity and resolution. But then we do many applications. And what I want to do is show you what NMR is, but in the context of some applications to energy materials. And of course, we are all aware of all the problems we have with energy at the moment, and it's extra clear in these very trying times, I would say. Obviously, we want to mitigate global warming and stop CO2 emissions, but we are far away from that. The Netherlands still produces 88% of its energy with fossil fuels. Only 12% is renewable. So we need good, reliable, renewable energy sources like wind, solar, tides, you name it. We probably need them all. And we look at the specific materials for solar cells, and I come to that. Then all of these sources are intermittent, so we need storage. And particularly if you also want to use it for driving, etc., we need portable storage. So we need batteries, etc. But on top of that, what shouldn't be forgotten is that we also should look at heat. So we should also be able to store heat and maybe use excess electricity to store it in chemical energy that we can then release as heat again. But overall, we want to avoid to put too much energy in heating and cooling buildings. And photochromic materials could play a role in that. And they are used, for instance, in smart windows, which work like sunglasses that simply get dark when the sun shines, so that you need to do less cooling. So let's go over one example for batteries a bit more in detail. So first we could ask ourselves, we already have electric cars, everything is there. So do we still need battery research? Well, let's ask Elon Musk.
Now, the issue with existing batteries is that they suck, okay? They're really horrible.
So, well, that answers that, I would say. Obviously, Elon was not talking about his own batteries, but still, also they suck to a certain amount. And that is because even today, 1/3 of the weight and the price of an EV comes from the batteries. And on top of that, there are quite some safety issues. We all know the pictures of phones that get fire on a plane, or Teslas that get into terrible fires, etc. So that is something you want to mitigate. On top of that, I mean, we should not just say, oh, we have lithium batteries. I mean, we have another problem then. We want to get rid of Russian gas, but then the next issue is, do we want to rely for 80% on Chinese lithium? So also there, we need to look at different chemistries and not depend on lithium alone. In any case, what is a very important hurdle at the moment to make batteries lighter and safer is the electrolyte. In current batteries, the electrolyte is essentially a liquid electrolyte that carries the ions over from the anode to the cathode and vice versa during charging and discharging. So there is really a worldwide search for efficient solid-state electrolytes that conduct lithium ions or other ions, but not electrons. And there that is a part of research where we also put a lot of effort in. And one example is a good material that had been identified. Actually, it has been studied for hydrogen storage, but it was found out that lithium boron hydride is a material that in the high temperature phase displays a very high conductivity. So this is the room temperature phase. It's an orthorhombic structure. So the red are the lithiums, and then we have BH4 groups, nicely in a crystal. But at higher temperature, you form planes of lithium through which the lithium can freely diffuse. And that we can actually see in our NMR, lithium NMR spectrum, which gives us some very broad line. But going to higher temperatures, we suddenly see a completely different spectrum. What this particularly means, I will discuss in a second. Sorry. But the problem is, of course, that this phase transition into this usable phase only takes place at a temperature of above 120 degrees Celsius. So as such, is much less useful. So people have been looking at different approaches to mitigate that. And actually one way, one thing you can do is to nano-confine the material. Actually, that was a serendipity discovery that we did with our collaborators in Utrecht. Our collaborators in Utrecht were working with nanostructuring of hydrides in carbon for hydrogen storage, and nano confinement in carbon gave us very poor spectra. So we asked them, can't you do it in silicon? And they made samples specifically only to do NMR, to look at LEBFR in confinement. But then at the same time, it came out that actually, because of this, the lithium mobility and therefore the conductivity in the nano-confined material was very high over the entire temperature range. So that was a really interesting discovery. And obviously now we wanted to figure out what's going on in these materials. What is really the structure of lithium BH4 in just porous silica? So porous silicas are just a silica, so SeO2, that has well-defined pores in there. And then this LeBO4 is actually melt infiltrated into the material. And remarkably, the properties of the system changed drastically. So we started to look, and that is, as I said, the nice thing of NMR is that we can look at the entire periodic system. And here we see some boron spectra as function of temperature. And even at ambient temperatures, we see that there are two overlapping peaks. And one of these peaks even develops some fine structure. And I chose this example because actually 3 important NMR interactions are present in this spectrum, which helped us figuring out what happens to lithium boron hydride nano-confined in silica pores. So first of all, so we have these different spectra, and the first thing is that they have a difference in chemical shielding. So I told you, we put the sample into an external magnetic field. So all the different atoms in the material see that magnetic field, but they don't see the full field that we apply, because the electrons that are around the nuclei in the atoms or in the ions in the structure, they respond to the magnetic field. And as a result, they shield off the magnetic. They oppose the field that is applied. And as a result, the nucleus feels a slightly lower field than the field we apply. And as a result, we see different resonance frequencies for nuclei that are in a slightly different environment. And this opposing of the field is, of course, very well known as diamagnetism. And I don't know who of you know about the floating frog experiment that was done in the magnet lab in Nijmegen, where they started with floating a frog above a magnet. So actually they floated the entire grocery store, and I have an example here of a tomato that is essentially weightless, floating above a magnet. And it's simply because all the electrons in the system respond to the magnetic field, so that you essentially generate currents that oppose the applied field. And in this case, the net result is that you can float a diamagnetic object above a magnet. And you can also do that with pure water droplets. So it's not that there are salts also moving here. It's really the response from the electrons. Okay, so in our case, when we look at our boron hydride in the silica, in the nanopores, we see that we have two different chemical shifts. And the chemical shift really allows us to identify different structures. For instance, different organic structural building blocks. That is what the organic chemists use to identify their molecules. The coordination of ions in inorganic materials, but in our case, they are both BH4. There can be hydrogen bonding to neighboring molecules, but in a solid, really the proximity to other molecules also induces a small differences in chemical shift. Because a neighboring group can also generate a tiny field that you see. And that's the chemical shift. So we see two different types of BH4 units in these structures. That's one thing. The next interaction that is very important, that's also present in this spectrum, is the spin-spin interaction. And the spin-spin interaction is simply that one spin feels the magnetic field of a neighboring spin. So we know the spin, so the orbital angular momentum can be seen as a tiny field. So when I have a certain spin J, a neighboring spin K will feel the field of J, and vice versa, J will feel the field of K. Well, in this case, when we look at the BH4 group, what we see is that we have, for lithium boron hydride, we have this one broad resonance. It's about 7 kilohertz broad, and we calculated the different options for the lithium boron hydride structure. And we found what this means is that in this case, the BH4 units, they are rapidly moving around their own axis. And that means there are no dipolar interactions of boron to their directly bound protons. But in a well-organized solid, where all the BH4 sit in a crystal lattice, still the neighboring BH4 units also couple to the boron, the protons of neighboring BH4 units couple to a given boron. That gives us this line width, and we can exactly predict that. So we call this the dipolar interaction. And actually that allows us to even measure distances between nuclei. So you can get very detailed information about the distance between different neighboring nuclei. And it's super accurate because it depends on the inverse of the third power of the distance. But then we have this line that's split into a little multiplet at higher temperature. Actually, it's a quintuplet. So 5 different lines. And this is now the so-called J coupling of the boron via a chemical bond, because these 4 protons, they bind with a chemical bond to boron, and so-called J couplings are couplings between nuclei that share electrons in a chemical bond. If there is no chemical bond, there is no J coupling. The interesting thing here is that in general, J couplings in solid state, well, they are hardly ever observed in the solid state because they are minute. And the dipolar interaction is always bigger, almost always bigger than the J couplings. But in this case, we see the J coupling of boron and protons, and this tells us that for this fraction of the material, the BH4 units are not only tumbling around very rapidly, they also diffuse through the whole material. So essentially, we have a fraction of BH4 that is a liquid, which is very strange, of course, to have a liquid fraction in a furthermore solid sample. So we looked again at the lithium spectra. And I showed you already the spectra of lithium BH4 in bulk, just the bulk matter. We have the low temperature phase, we have the high temperature phase. There is only one lithium site, but they have very strange spectra, as you see. There is a central peak, but there are also these broad features. So what is this? Well, this brings us to the fourth interaction that we have in NMR, and that is called the quadrupolar interaction. And this quadrupolar interaction is, again, complicating things further. I talked about spins that can be spin up or spin down, but actually nuclei can have many more spin quantum numbers. They can have spin 1, spin 3 halves, actually up to spin 9 halves. And that means they are not only just spin up and spin down, they can have multiple orientations from -I to +I, increasing by steps of 1 in the magnetic field. So for a spin 3 halves, lithium 7 is a spin 3 halves, there are 4 possible different orientations of the spin in the magnetic field that are so-called eigenstates. On top of that, these so-called, we call them quadrupolar nuclei, this nucleus is not a little sphere. It can be an ellipsoid or a pancake. And that means, depending on the charges that surround the nucleus, different orientations of the nucleus will, say, be energetically more or less favorable. And that causes all these energies levels to shift. And as a result, that from a single side, we get a spectrum with multiple features like this. So now when we revisit this lithium spectrum, for the bulk, we know that here we saw that the lithium actually is rather rigid. And in the high temperature phase, it moves about. And that gives us this nice, say, textbook example of the line shape, as I just showed you. But for these melt-infiltrated samples, we get all these line shapes in between. And again, is this one lithium species or are there multiple? And for that, we resorted to 6 lithium. 6 lithium NMR only has a very small quadrupolar interaction. It's not noticeable in the spectra. And then we looked at the chemical shifts again, and that proved that in all these melt-infiltrated samples, actually we have two types of lithium as well. And we did a lot of calculations. I'm not going into details, but by assuming that the lithium can exchange between the two fractions, particularly when you increase the temperature, we can get line shapes actually that are similar to these line shapes that we observe. So we see also that the lithium is moving about and how it is moving about. So then the next step I'd like to point out, and we also use that for this study, is that NMR is not confined to just one experiment. Get a spectrum, do this radio frequency pulse, measure your signal, and generate your spectrum out of that. Actually, in the 70s, George Jenner, he proposed that you could do multiple radio frequency pulses and define different time dependencies between these pulses and vary them in a systematic way. And in that way, you can, for instance, create two-dimensional spectra, something like that, where you would have peaks mapped out in 2 dimensions. Well, we hardly ever look at such plots. We plot so-called contour plots. And this allows us to correlate different spins to each other. So spins that are, for instance, bound because they experience a J coupling. But also you can map out different interactions of a single spin. For instance, see what is the chemical shift versus the dipolar interaction, or the chemical shift versus the quadrupolar interaction, etc. And that this really has made NMR to this extremely powerful analytical technique it is these days. And actually, quite interesting, George Jenner just proposed this as a summer school, but never did anything with it. And then Richard Ernst took up on this idea, and he fully developed the methodology, which then gave him the Nobel Prize in 1991. So you see, NMR-related research gets lots of Nobel Prizes. Okay, so we also did two-dimensional NMR, and now I revisit the Bohr spectrum of the BH4 unit again. And there we can see in a so-called exchange spectrum that when we do such an experiment, we can correlate the Bohr shifts in 1 dimension to the Bohr shift sometime later. If there is no time in between, of course, nothing happens, and we see the signal on the diagonal of this 2D spectrum. However, if we allow a certain time between these periods, we get a spectrum with so-called cross peaks. And that means that BH4 units go from this highly mobile phase to the more rigid phase and vice versa. And the most exciting experiment we did is where we we cranked up the temperature in this time between the periods where we connect the chemical shift to each other, and then we see it becomes asymmetric. And this tells us that one phase grows at the expense of the other phase. So actually going to a higher temperature, we see that we get more of this mobile phase, and that there is exchange of the different ions between these phases. And that brings us to the complete picture, well, more or less complete. So suppose the green striped area here is the silica pore. It's corrugated, and the lithium boron hydride gets infiltrated into this pore. And what we now have as a model, which fits all our data, is that you get in the center of the pore, you get a rigid fraction, which is the regular bulk matter. But around it, the lithium boron hydride cannot, say, crystallize. And it remains fluid. And that means that both the BH4 units and the lithium units, they freely move through this shell, whereas in the low temperature, inside this solid core, hardly anything happens. And only at elevated temperatures, when we go above the phase transition temperature of the lithium boron hydride, also lithium and boron hydride start to move in this solid phase. And then there is free exchange of lithium and BH4 units between these two phases. But already here, we have material that can conduct lithium extremely efficiently. So then we ask ourselves, yeah, why is that? Why do we get this liquid shell? And we started to look at the silica spectra. And the black spectrum here is the spectrum of a regular silica. And we see 3 resonances, which essentially tell us about how condensed the SaO2 is. And there are OH groups at the center. We can do 2D NMR, where we correlate the silicon spectrum to the proton spectrum, etc. But it's very important that we find a completely new site. And by bringing all this together, we could essentially postulate that at the pore wall, actually the lithium borohydride reacts with the silica. The surface of the silica gets reconstructed, and we form a completely new structure where we have a hydride, where essentially the BH4 is associated, and then the SiOHs, the silanols that are there, probably exchanged with lithium. And because you have such groups and the corrugation of the pores, that is probably the reason behind the fact that you have this very dynamic fraction, this liquid-like fraction in a solid material. But it's extremely useful because that can guide us to potential solid electrolytes that would have much less problems with safety issues. So I see that I almost spent all of my time, so I will quickly tell you a little bit about the photovoltaic materials we work on, but without going into any NMR details. But I think it's interesting to know, and I want to show you this little graph. This is essentially the Olympics of solar cells. And it shows all kinds of different sites and different materials that have a certain efficiency in solar conversion. And of course, here you have very efficient cells, but these are multi-junction, gallium arsenide cells, etc. They are super difficult and super expensive to make, but they can have big records, but they are essentially only interesting for applications in space, where you need super lightweights and super high efficiencies. But when we look at these blue curves here, this is development of our silicon panels that many of us have on our roofs. But about a decade ago, a new material was discovered, and they are called hybrid halide perovskites, and these are the red-yellow ones here. And they went from an efficiency from a few percent to an efficiency that already outperforms polycrystalline silicon cells. And this happened in a decade, whereas these silicon cells, they were developed for 50 years and they are above 20% now. And these materials, the base structure is methyl ammonium lead iodide. It has can be made to have a super high energy conversion efficiency. It can be processed at ambient temperatures. So silicon, you need to process at high temperatures, what have you. No, these materials you can simply make by mixing methyl ammonium iodide and lead iodide. You mix it and you have the perovskite. And all these elements are earth abundant. So that's very promising. I mean, there are also issues. Obviously, there is lead in there. That is something that is not something we like. Moreover, they are not fully stable, particularly they are sensitive to air and moisture. So that is something we need to work on. But again, we are doing NMR to figure out how they work, essentially. And the whole issue is that they are super dynamic structures. So you have interesting phases. You have lead iodide octahedrons. And there are different phase transitions. The interesting material is the cubic phase at higher temperature. the regular material actually is not cubic at ambient temperatures, but by playing with the composition of which cations you put in there, you can force it to become cubic, which is quite intriguing. But there is an interplay between this inorganic, say, lattice, and the cations. As I said, it's methylammonium, so it's an organic molecule. And there is this nice interplay and dynamics going on. And this is exactly where the strength of NMR is. We can look at the resonances. We can study all of the different isotopes. We can do carbon NMR. We can do proton NMR. We can study nitrogen, nitrogen-14. We can study lead. We can even look at the iodine. And then you don't even need a magnet because the internal, this so-called quadrupolar interaction is so big that you even don't need a magnet. Okay, so let's not go in all the details of the spectra, but we figured out that when you have mixed compositions, which are used of the cations, that there is a certain clustering, that this is not a uniform random distribution of the methylammonium and the so-called formamidinium. We can really figure out that there is a variation in say, occurrence of different sites, and essentially the cations like to sit with equal kinds. So methylammoniums like methylammonium neighbors, and formamidiums are like other formamidiums. So just like people. Okay, and then we also looked at halide mixing. Again, we can do the lead NMR, and here we find now that based on the dipolar interactions, that again, the mobility of the cation is influenced by the composition of the lattice. We find nice, say, random mixing of bromine and iodine in this case. But when we now look at the dynamics of the methylammonium, it doesn't rotate completely random anymore. And we can tell so from our NMR spectra, and our theory colleagues can now also simulate that in these so-called molecular dynamics simulations we see here. And you see that essentially the CN axis stays in a certain direction for a long time. And this is depicted here in these heat plots where depending on whether bromine or iodine are surrounding the methylammonium, they more or less give it a preference in its orientation. Okay, so we learn a lot about NMR here. So where are we going? We want to get this in-depth information, and the next step is that we want to study these materials under illumination. And that is, I said, we are still working on the methodology, and doing operando NMR is an important challenge for NMR, so that we can do, for instance, chemical reactions in the magnet, or indeed put a photovoltaic material in the magnet, illuminate it, and look at the response so that we understand on a molecular level what's happening in the material. So I leave it at this. Let's skip the smart windows. As I said, they work like the coloring sunglasses that we have. So here are the people that all do the energy-related research. I'm not going to name them all, but the battery material was done by Sander Lambrechts, and we collaborate with Utrecht. The Perovskites were done with Helen Gruninger, who was a postdoc in our group and is now in Bayreuth, and we collaborate with Bayreuth and the theoreticians from Twente to do this work. And finally, the smart windows work was done by Shrestha, and there we collaborate with the University of Delft. And then we have other battery projects with the Chinese group, and that is Hong Tao, who does that kind of work. But I'll leave it at this. I thank you for your attention. I hope I didn't do it like this guy. And I'm open to take your questions. And if things were too unclear, I will try to give an intelligible answer. So thanks again. And I would say go ahead and ask questions.
Okay, thanks for listening, and everyone enjoy your evening and stay healthy. Goodbye.
Bye.